Yes, Victor.
Perfect. All right. So today we'll continue, inshallah, chapter 5, just few sections, and before we start talking about chapter 6. Now, in chapter 5, the last thing we were discussing in chapter 5 is simply in polar reaction, we do have two species. One we called it nucleophile, one we called it electrophile. And as we said before, the whole chemistry is all about interaction between nucleophiles and electrophiles. Most likely, in most of chemical reactions, in most of polar chemical reactions, we do have nucleophile species attacking electrophile or vice versa. So the nucleophile, from its name, we said it is either to be a negative, a formal negative species, any negative ion, or it could be a formal negative. What does that mean, formal negative? It means simply a molecule which contains an atom which has lone or lone pair. Okay, imagine. All right, again. So the nucleophile, it could be a formal negative, any negative ion, or a neutral molecule contains lone pair or pairs of electrons. So, for example, any ion, negative ion such as Cn minus, like Br minus, like CH3O minus, any anion is a nucleophile. Or, for example, H2O, ammonia, alcohol. You see, you can consider these atoms here, the atoms which contains the lone pair, we can consider them as nucleophiles. I did record the lecture, don't worry. Do you follow me, guys? So this is simply the definition of any nucleophile. So any nucleophile, in order to recognize where is the nucleophilic part in any reaction, it's supposed to be any negative ion or any neutral molecule such as water, ammonia, alcohol, amine maybe, for example, amine, and so on and so forth. So the most important thing about the neutral molecule, in order to be considered as nucleophile, it must contain an atom which contains a lone or lone pairs. While electrophile, as we said, is any positive or ion, which is the cation, do you follow me? Or simply a neutral molecule contain, let's say, potential deficiency of electrons. Let's say not contain, which has a potential deficiency of electrons, such as, for example, of course, any positive ion like sodium, like anything like, for example, CH3 plus, anything which is positive ion, or for example, aluminum chloride, which is the Lewis acid here, aluminum chloride, BF3, these Lewis acids, you can see the boron here, or the aluminum, it contains less number of electrons than usual, which is the usual here, the octet number of electrons, which is supposed to surround boron or aluminum, supposed to be 8, but as you can see in these little structures, they have actually less number of electrons. This is all about the electrophiles and the nucleophiles in organic chemistry. Of course, the next lecture, the next chapter, when we start talking about reactions of alkenes, we will simply use these concepts when we draw the mechanism of the reaction. So for anything which is related to the mechanism of the alkene, we will just postpone it to the next lecture. Let me just highlight something before I start talking about the next chapter, or which is chapter 6. Let me talk about the energy diagram in any organic reaction. Energy diagram in organic reactions. In any organic reactions, this is the energy diagram, which is always the case. Now, for example, if we are talking about exothermic reaction, the reactant will be at certain point of energy. This is the energy, and this is the reaction coordinates, or the progress of the reaction. So if we have the reactant at certain amount of energy goes to product. In this case, what's the status of this reaction? Is it exothermic or endothermic reaction? As I write it here, so the reactant will go to the product, and this is the energy. Are we talking about exothermic or endothermic reaction? X, of course, because simply the product is less energy than the reactant. Now, in any type of reaction like this or any other reaction, there will be always increase in energy where the reactant must go or must reach this point, which we call it, this amount of energy, we call it activation energy. In any reaction, there must be, regardless if the reaction is exothermic or endothermic, there is always certain amount of energy needed to achieve this point. And in this point here, the reactant will go to what we call a transition state. Now, and then later on, this reaction can, for example, proceed to somehow intermediate, a little bit more stable intermediate, and then the intermediate go maybe to the product. This is always the case like that. So, what do we mean by this energetic coordination? It's like this. Actually, in any reaction, we may think about it as if it is a collection of bond making and bond forming. Now, in order for the reaction to take place, there is always certain amount of energy needed for this reaction. It must take in order to be able to go to the product, regardless if the product is less energetic than the reactant or high. Of course, as you studied before, this difference in energy between the reactant and the product, we call it the delta H of the reaction. This is the delta G naught, let's say, what we call it the activation energy, which is needed for any reaction. That's always the case actually in any reaction. All right, I will change it. So if this is not clear, all right, I will just redraw it again. So this is the energy, and this is reaction coordinates. So we have studied actually, or we discussed an example of exothermic reaction. So the reactant is at this level, and the product is at this level. There is no reaction going directly like this. Never, ever, even if it is exothermic reaction. There always, whatever the reaction is, either if it is exothermic or endothermic, there must be always increase in the energy, then going backward if it is going downward or upward, doesn't matter. You follow me? So why we need this? This is actually the energy, what we call it the activation energy. It's the energy needed actually for the reactant to, let's say, to take the needed velocity for collision, the orientation of collision. All of this you may study it in more details in physical chemistry, but anyway, there is always increase in energy, and then maybe there is some drop in energy if there is a formation of what we call it intermediate. And then there is again increase in the energy. So here, the energy needed here, this is what we call it the activation energy. And this, as we said before, the difference in energy between reactant and product, this is what we call it the delta H of the reaction. That's actually the coordinate of any reaction, which we always refer to a reaction. Either, as I said, if the product is less energy than the reactant or higher, it doesn't matter. Always there is increase in the energy. Is that clear? Is there any question about the reaction coordination and how we represent it? Is there any question about it? Any question? All right. So let's start with the alkene, which is chapter 6. Again, if you have different edition, you just please follow the topic. Here we are talking now about chapter 6, which is the alkene, its reactions, its activity, and so on and so forth. So chapter 6. Chapter 6, alkene, about its structure and reactivity. I'm going to skip the few slides about the history, about the industrial importance of the alkene, just to not to make the lecture too much long. I'm just going to focus right away on the thing which need to be discussed actually. First of all, as you know, the alkene is as a functional group. Any organic compound contains a double bond, double bond carbon. This is what we call it, the alkene. So first, before talking about the alkene, let's talk about degree of unsaturation. Degree of unsaturation, or sometimes in certain textbooks we call it index of hydrogen deficiency. In principle, as we said before, any alkane, if we have a saturated hydrocarbon, the general formula for it will be CnH2n plus 2. Do you follow me? While in any alkene, for the formation or the presence of let's say, the presence of carbon, double bond carbon in any compound will reduce number of hydrogens in the formula by 2. Always. For every or for any carbon, double bond carbon, the general formula of the compound will be reduced, or the number of hydrogens will be reduced by 2. In other words, let's take, for example, alkane. Alkane, we have CH3, CH3. This is ethane. And the general formula for this is C2H6. While the simplest alkene ever, which we are going to discuss, which is the ethene, for example, CH2 double bond CH2. The general formula of this compound is C2H4. As you can see, if you focus on the number of hydrogens, in the ethane we have 6 hydrogens for 2 carbons, while in the ethene we have 4 hydrogens for 2 carbons, which means we have here less number of hydrogens by 2. So for any carbon, double bond carbon, there is always a loss of 2 hydrogens all the time. Do you follow me? Is that clear? Now, for a general formula, like the general formula what you have actually in the slide, if you have, for example, for example, C6, here the formula is supposed to be C6H10. If we are talking about a compound C6H10, first of all, once we see this compound or this formula, we must conclude that this is most likely to be unsaturated. Why it is unsaturated? Why this compound must be, or this formula must be unsaturated? Because if it is saturated, with a saturated organic compound we know, if it has C6 carbons, then the number of hydrogens is supposed to be 14, which is 2n plus 2. Isn't it? It is 4 hydrogens type, not 2. Do you follow me? There is a missing of 4 hydrogens, not only 2 hydrogens. Because the saturated organic compound we know, or the general formula for fully saturated organic compound, which is the alkane, supposed to be CnH2n plus 2. Is that clear? So in this case here, as you can see, we have in this compound 10 hydrogens, but the saturated one, this is saturated. The number of hydrogens must be 14, but in here we do have only 10. Then definitely we must conclude that this compound to be unsaturated. Now, in general, for missing of, or for every 2 hydrogens unsaturated, for every 2 hydrogens missing from the saturated formula, there is a conclusion. We may conclude that either we have a cyclic system, cyclo, or double bond. For every 2 hydrogens missing, we may conclude that either we have a cyclic system, a cyclo, or a double bond. What does that mean here? Here, as you can see, the difference between the hydrogens of the saturated to the unsaturated, there is 4 hydrogens missing. If you divide by 2, that means the degree of unsaturation here in this compound is 2, which means the 2 unsaturation here means 2, that, let's say, degree of unsaturation, let's just agree on something. Degree of unsaturation, let's call it DOU, degree of unsaturation. So the degree of unsaturation is equal to, it means we may conclude that we have 2 cyclic systems, or 2 cyclic systems, or we have 2 double bonds, or we may have 1 cycle, 1 double, and 1 double, or we may have triple. So these are actually the 4 possibilities for this formula. So once we know this formula, C6H14, we may conclude that we have inside this formula, in this structural form of this compound, it must contain either 2 cycle system, or 2 double bonds, or 1 cycle and 1 double, or triple bond, because that's actually the meaning of the unsaturation of this formula. Is that clear, guys? Is there any question about the degree of unsaturation and what should we expect actually to have in this structure of this compound? Is there any question about it? All right, so this is simply how we should know. So you can just check the compounds here. For example, for every possibility here, you may think of, for example, we have 6 compounds, 6 carbons here. For example, I may draw here to be 2 cyclic system. I may have, for example, as you have it in the slide, I may have that like this. For example, this compound has or fulfill the general formula of C6H10. 2 double bonds, I may have it, for example, like CH2 double bond CH, then CH double bond CH2, then CH2, CH3, sorry, CH. You follow me? So in this case here, we do have two double bonds inside the compound, or one cycle and one double. For example, I may have it like this. A triple bond, I may have it, or I may draw, for example, CH triple bond C, CH2 by, for example, 3, and then CH3. 4, yeah, 3, 4, 5, 6. Right. So these are actually the possibilities of the compound. Yes, Khalaf, you can see, you can view it later. It doesn't matter now. If you're facing a problem in the internet, is fine. Now, but anyone else, anyone has a problem, has a question about this? How you can guess what are the structural formula of the compound from the molecular formula? So this knowledge you all must know. You should be able to guess what could be the isomers or the possible isomers or possible isomeric structures of a formula from its formula by calculating the degree of unsaturation on any compound. Do you follow me? All right, let me just give you another example. Let's see. Is there any question so far? All right, let's see, for example, C6H6. What would be the degree of unsaturation of this compound? Just calculate it, please, all of you. Calculate the degree of unsaturation, please. What would be the degree of unsaturation of this compound? Equal how much for C6H6? Exactly, it is 4. Which means we have high degree of unsaturation. Then what are the possibilities? Please give me any possibilities. What are the possible structures actually of this compound? What could this compound or must contain? Just write down. How many cyclic system Muhammad must contain? It must contain. Yes, this is one possibility, to be containing 4 cyclic systems. But of course, from our general knowledge, to have 6 carbons with 4 cycles, it's almost difficult to guess it. But we can, for example, say, this can be. There are different possibilities, of course. Just I'm talking about the ultimate possibilities, like 4 cyclic system or 4 double bonds. Or, for example, 2 triple bonds, because every triple bond is like 2 double bonds. Or now 1 cycle and 3 double. Or, for example, 2 cycle, 2 double, and so on and so forth. You may draw it. But anyway, one of the best possibilities, or one of the most possible guess, actually, this to be 1 cycle system and 3 double bonds as in benzene system. So actually, in principle, that's actually for your knowledge. In principle, whenever we have the degree of unsaturation is 4 and more, the most possible structure to be actually benzene and its derivatives. Do you follow me? Because the benzene has actually 4 degree of unsaturation. Now, the question is, what if we have molecular formula contains other than carbon and hydrogen? For example, we have it containing oxygen or sulfur or nitrogen and halogen and so on. For example, suppose what's the degree of unsaturation of C5H11 H10 actually. H10 BRNO, for example. What's the degree of unsaturation of a molecular formula of this compound? In this case, it will become a little bit difficult actually to calculate the degree of such unsaturation, but I'm just going to use or to write to you a rule here which can be easily calculated. The degree of unsaturated equals to 2C plus 2 plus N minus H plus X over 2. This is simply how we can calculate degree of unsaturation all the time. Can you see it? The degree of unsaturation, regardless of the molecular formula, we can always calculate it by this way. 2C plus 2 plus nitrogen minus hydrogen minus X over 2. What does that mean? If you have a nitrogen here, then you must always add the number of hydrogens. And here we subtract hydrogens, and then here we subtract halogens, and then we divide by 2. Let's just calculate it for this. It will be 2 times 5 plus 2 plus the nitrogens here we have 1 minus the hydrogens here we have 10, and then minus 1 over 2. Again, I'm just going to take this off. Here, the degree of unsaturation of this formula will be 2 times 5 plus 2 plus 1 for the nitrogen minus 10 for the hydrogens minus 1 for the halogen, and then over 2. And then you just have to do the calculation. 2 times 5 is equal to 10, plus 2 means 12, plus 1, 13, minus 10, 3, minus 1, 2, over 2 equals to 2. So which means we have 10 plus 2 plus 1 minus 10 minus 1 over 2, which means the plus 1 with minus 1, and then we have 2 over 2, which equals to 1. So the degree of unsaturation of this formula is equal to 1. Yes, Rahma. That's actually, as you can see, Rahma, as Rahma mentioned, we always ignore the oxygen. Exactly. That's only here, you can just even extend this formula or this rule for the calculation of the degree of unsaturation for any atom actually in the compound. As you can see here, nitrogen is a representation of group number 3, and hydrogen is hydrogen, of course, and halogen is a representation of group number 7. So whenever you have a halogen here, we always subtract it from the formula. Any nitrogen, we always add it to the formula, as you can see, and any oxygen, we do not represent it. So this is in order not to be there. So in the degree of unsaturation, we don't consider our number of oxygens is not affecting degree of unsaturation. Only atoms in group number 3 and group number 7 can be calculated in that. Do you follow me? Simply because actually Rahma, because simply oxygen is divalent, it simply contains 2, so it will not affect the number of hydrogens. The only atoms which are affecting the degree of unsaturation are group number 3 and group number 7. So as you can, let me just give you another example. For example, C9H12 P3 sulfur. Do you follow me? Muhammad, just ignore this question now for the time being. Just focus on the rule here, how to calculate the degree of unsaturation. You follow me? Now, in order to calculate the degree of unsaturation of this compound, it will be 2 times 9 plus 2 plus Now, is there any nitrogen or any atom which present in group number 3? If you check here, the phosphorus in group number 3, so therefore we must add 3, which is actually corresponding to the presence of 3 phosphorus. Now, is there any halogen? No halogen, so we just minus 12. Then the sulfur here has no effect, or group number 3 has no effect in the degree of unsaturation, and then divided over 2, which means we have 18 plus 2, 20. Sorry, then it must be then. So this must be 11. Sorry, just make it 11 here in order to make the correct formula. So we have it minus 11. So again here, 18 plus 20. 23 minus 11, which is equal to 12 over 2, which means 6. The degree of unsaturation of this compound is equal to 6. Do you follow me? Is that clear, guys? Is that clear how to calculate the degree of unsaturation of any organic compound from its formula? Yes, please.
What about sulfur?
Yeah, this is what I'm saying. Number of oxygens, or ignore, let me just say it like this. Ignore any atom from group number 6. So sulfur is group number 6, so we don't count it. خلاص. As if it is not there. Like oxygen. Do you follow me? We do not count, we do not include the number of any atom in group number 6 in our calculation for the degree of unsaturation. Do you follow me? So sulfur is in group number 6, so we don't count it. You follow me? But phosphorus, it's in group number 5, so we count it as the nitrogen in here. So you can say this is here applies for any atom in group number 3, or this here applies for any atom in group number 6. Is that clear, guys?
Yes, Victor, thank you.
Sure, sure. Any other question about the degree of unsaturation? Now, you should not ever hesitate to calculate the degree of unsaturation of any compound, because here you have a generalized formula to take this into consideration. Now, the most important thing actually, as soon as you calculate the degree of unsaturation, is simply your thinking is to guess what possible isomeric structure can fulfill this condition or this degree of unsaturation. Do you follow me? So that's here, when I know that the degree of unsaturation is 6, then I should expect that this compound to be highly unsaturated. Do you follow me? As we will see actually in the coming point, or in the coming slides of the topic. Now, let's move to slide number 11, which is about, if there is no question about degree of unsaturation, I'm just going to move to slide 11, which is the naming of alkenes, or IUPAC nomenclature of alkenes. Is there any question about degree of unsaturation, how to calculate it, or what could we conclude from the degree of unsaturation? Any question about it before we move to slide 11? All right, so let's move then to slide 11, which is the IUPAC nomenclature. Is there a question? All right, IUPAC nomenclature of alkene. IUPAC nomenclature of alkene. Now, in the IUPAC nomenclature alkenes, the first rule here, it will apply. We must choose the longest continuous chain of carbons containing the alkene functionality, which is carbon double bond carbon, the two carbons. Do you follow me? This will be, or the parent name then, or simply change or replace the final ane in the corresponding alkane. Let me say it like this: replace the final ane and corresponding alkane by ene to represent or to show that we do have alkene functionality. Let me just give you an example for this. CH3, CH2, C double bond, CH2, 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 CH3. So in this example here, what's the longest continuous chain of carbon atoms here? In this example. How many? What's the length of the continuous chain of carbon atoms? 7. Do you follow me? As Mazen said it's 7, which is simply this carbon atoms, isn't it, Mazen? And Rihan, they said 7. Is there any other questions? Maria said 6. Which is actually 6. Maria, again, I'm sure she means here. Do you follow me? So this is Mazen and Riham, yeah, Maria and Al-Zawur and Taif, they say it's 6. Now, which one is correct? This length is 7 carbons, this length is 6 carbons, and this length is how many? 5 carbons. I think we all agree that this is wrong, but which one we should choose, the 7 or 6? 6 carbons or 7 carbons to be the longest chain? We must choose 6. Why? Because here, always the case, by the way, from now on, in any chapter containing a functional group, the rule of IBAC becomes like this. We must choose longest continuous chain of carbon atoms which contains the functional group. Here, we're talking about alkene functionality. The alkene functionality is both carbons, the carbon double bond carbon. So both carbons must be part of our longest continuous chain of carbon atoms. Now, if you choose 7, this is definitely wrong, because 7, it contains only one of the 2 of the functional group, which means definitely this is wrong. That's why actually the correct longest continuous chain of carbon atoms must be number 6 rather than to be 7. Is that clear, guys? How to choose the longest continuous chain of carbon atoms? Perfect. So in this case here, as you can see, our parent name in this case will become what? Because 6 carbons is the corresponding alkane is hexane. Now we must replace the final ane by ene. Therefore, our parent name definitely will be hexene. Do you follow me? Right. That's actually our parent name. Now, the second rule here, we must then number the chain closer to, and this is always applied from now on, from this chapter and going on, always after you choose the longest continuous chain of carbon atoms which contains the functional group, then we must number the chain closer to the functional group regardless of other substituents. Do you follow me? Unless you may simply can take this into consideration and give them the lowest possible number. Do you follow me? So in this case here, what we have, where we must number the chain, shall we number it from this side, from the right, or from downward here? Where shall we start numbering the chain? Down, of course, because in this case, when we number it from here, we will give it the lowest possible number. 1, 2, 3, 4, 5, 6. So in this case here, after you number the chain, you must designate the location of the double bond. In this case, always we designate the alkene by its lower number. Because remember that this functional group which we are talking about is composed of 2 carbons. So there should be 2 numbers. We always designate the location of the alkene by the lower number. So in this case, our hexene here is 1 hexene. Do you follow me? So always designate the location of the double bond by the lower number. So I may write these rules maybe if you wish. Number the chain. Closer to carbon, double bond carbon, and then to give other substituents the lowest or the lowest possible number by the rule. I'll come to this maybe with more examples. Third, designate the location of the carbon double bond carbon by the lower number. So these are the rules, and then the rest of the rules of the APAC. Intisar, I'll come to these questions after I finish the lecture. Now let's focus on the lecture. Don't talk about the exam now. Alright? So these are simply the rules for the nomenclature. So if you want to continue now the name, so this name of this compound will be then what? We have at position 2 this group, which is the ethyl. So we have 2 ethyl, then 1 hexene. Or in some of the textbooks, we may draw it or we may write it like this: 2 ethyl, hex, then 1 ene. So both are correct, both are the same name of the same compound. Yani, in other words, this number here, it reflects or refers to the location of the double bond, which is represented by the ene. So either we put it directly before the ene or before the parent name. Either here or there, it's both are correct. Is that clear how we draw it? How we write it? So you may write, or you may put, find both actually in your in your book or in other textbooks, but both are correct. All right. So these are actually, there are plenty of things, but here you just have to practice and see some specific rules about it. But anyway, let me just give you another example very quickly in order, before simply moving to naming or nomenclature of cycloalkenes. For example, here we have CH3, double bond, CH3, CH, CH, CH3, CH3, CH3. What should be the name of this compound? Please write it down. Try it very quickly, all of you. Of course, give me the full name, not just partial fractions of it. Anyone? I'm giving you 30 seconds exactly in order to answer this question. Perfect. Before the 30 seconds. Anyway, now the correct answer here, we must start from this side, 1, 2, 3, 4, 5, because simply if we start from this side, it's actually closer to the double bond, therefore the name here will be 2,4,4 trimethyl 2-pentene. So this is the correct name, 2,4,4 trimethyl 2-pentene. All right, let me just comment on some of your answers. Now, since we have trimethyl, then we must have 3 numbers. We have 3 substituents, for example, or here, sorry, maybe just this one and this one. All right? We have 3 substituents, therefore we must have 3 numbers, because always remember my words, every substituent must be designated by a number. Do you follow me? Secondly, that we must start from this side because it's closer to the carbon, double bond carbon. Anyway, as I said, there are a huge number of examples. You just please go ahead and do as many as you can. Now, is there any question about this? Is there anything which is not clear about the name and why we chosen that? Any question about it? Riham, what do you mean by your question? تكرر رقم what do you mean by your question? Yes, Riham. Riham means, should we repeat the number? Yes, Riham, and everyone else. This is very important question, Riham. Everyone else, please remember this. Every substituent must be designated by a number, unless there is no need for it, which is very, very limited examples in the organic chemistry. Do you follow me? Every substituent must be designated by a number. If you have 10 substituents, you must have 10 numbers. Get the point? Is that clear, Riham? Wonderful. All right, so let's move a little bit to another aspect of the nomenclature, which is the nomenclature of cyclic system. The cyclic system is the same like what we have said about the nomenclature of cycloalkane, but the difference in here, it will be only cycloalkene in this case. So here, this will be cyclohexene. We add only cyclo before the name of the cyclic system, and then we add the corresponding alkene. So we have cycloalkene. Again, here the rule must be always the case. Let me just give you directly few examples. What's the name of this compound? Very quickly. Hurry up. I'm not going to write the rules because the rules are written already in your book, so you just can follow them up. I'm just going to practice with you some of the examples and to discuss any aspects of these examples. Just write down, please, the name of this compound very quickly and careful, of course. You have, again, 30 seconds. Thank you. All right. Actually, the correct name is Maria. It's 3-methyl cyclohexene. This is 3-methyl cyclohexene. Why? The correct name. The correct name is 3-methyl cyclohexene. Anything else is wrong. Do you follow me? It must be 3-methyl cyclohexene. Why? Because, again, in a cyclic system, now, whenever you have a functional group in a cyclic system, you must start numbering of this functional group and give it number 1. So we must start at this carbon here. These are the carbons which represent the functional group. We have this carbon and this carbon. So we have two options actually. Either we start from here, we say 1, 2, 3, or we start from here, we say 1, 2, 3, 4, 5, 6, for example. Do you follow me? So which one is more accurate? The first one or this one? The first option or the second numbering? First numbering or second numbering? We must start always from the double bond. Of course, it must be number 1 here, because here we will give the substituent the lowest possible number, in this case, which is 3-methylcyclohexane. But if we proceed this way, we will give the substituent here methyl number 6, which is, according to the logic of the IUPAC, is totally wrong. Because always, as I said, the motto of IUPAC is always to give the substituents the lowest possible numbers by the rule. So after you apply and give the priority for the nomenclature or the lowest possible number for the functional group, then we must take into consideration the lower possible number of the substituents. Do you follow me? So the correct number, or the correct name of this compound is 3-methylcyclohexane. Give you another example. What's the name of this compound? Very quickly. The name of this compound. – 30 seconds as usual. You have. Okay, the 30 seconds are finished. All right. Please let me write down the correct name, and then we can discuss what should be the name here. It will be actually 1, 2, 3, 4, 5, 6. So it will be actually here must be 5 bromo, 4 dimethyl cyclohexane. Either you add 1, or if you didn't add 1 is fine. Do you follow me? So it is 5 bromo 4 dimethyl cyclohexane. All right. I have seen plenty of your answers and many of you trying this. Let me just highlight first one thing. Please focus with me. Now, always in the carbon double bond carbon or carbon triple bond carbon, these functional groups contains 2 carbons, right? We must start in the cyclic, in any long chain, we must start numbering closer to these carbons. Do you follow me? To the double bond. Okay, I will answer all your questions right away. Just please focus with me and just think of the logic of the nomenclature and the numbering of the alkene. And in any nomenclature, we must start for the double bond, carbon double bond carbon. We must start numbering closer to the carbon double bond carbon in a chain. Do you follow me? And we must give the next carbon the second name. We had something called common names, and these common names are just because the number of compounds, organic compounds, which were known at that time were very limited, and therefore the chemists were using some common names, names without any scientific rule or systematic rule to derive them. And most likely these common names were generated from the scientists who discovered this compound, or from even the city where this compound has been discovered, from many aspects. But later on after that, when the chemistry starts to boom a lot, and we have to expand a lot, actually we have a huge number of compounds has been discovered, there was a huge need, a vital need to set a rule or set a systematic rules how to derive a name, or the same name, unified name for the same compound by all chemists. That's actually why we have IUPAC names. So for example, this is ethene, known by all chemists, but ethylene is a common name. So, but in principle, you are required to memorize some of the common names which are mentioned in the textbooks in this chapter. For example, the ethylene, the propylene, the isobutylene, the isoprene, these common names you are requested to know or to memorize, besides your ability or your knowledge to know the IUPAC name of every compound. Is that clear? Is that clear? Perfect. All right, let me just move to one aspect and then we'll stop our lecture, which is about the rotation, cis-trans isomerism in alkene. Now in alkane, we said previous time, when we have alkane, for example, we have always free rotation around any sigma bond. But the difference between sigma bond and carbon double bond carbon, free rotation is prohibited, is not allowed in carbon double bond carbon. So there is no rotation around carbon double bond carbon, because this rotation will break up a bond, and of course always breaking up a bond first needs a lot of energy, second it's not stable, because as we said, always the ultimate goal of any process actually to form more bonds, actually it's not to break up bonds. Do you follow me? So the difference between alkene and alkane is that around carbon double bond carbon, free rotation is prohibited, is not allowed, while around carbon single bond carbon, free rotation is allowed. And therefore here, this is actually what will result in what we call it the conformation. It will form what we call it, or what we have discussed in chapter 4, the conformations, or chapter 3, conformation, like staggered and eclipsed, for example, and so on and so forth. But in here, there is no free rotation. Now, because of the restricted or the prohibition of free rotation around carbon double bond carbon, we have a new type of isomerism, which we call it stereoisomers, which are actually cis-trans isomers. So for example, now when we have two substituents here, for example here, we have a methyl, hydrogen. There are two, because of the restriction for the free rotation around carbon double bond carbon, we have two compounds which can have the same formula, CH3, then hydrogen. So these compounds, these two compounds here, this we call it cis, and this we call it trans. The cis in here, around the carbon double bond carbon, when the two groups are in the same phase or in the same plane.